the second to last lecture in my series. Today I'm going to be talking about extra dimensions. I'm really looking forward to this one. It's a different kind of a lecture. Surprisingly, to a large extent, it really doesn't really rely much on the previous lectures, and it doesn't, for the most part, relies on Newtonian classical physics that you all should be at least a little bit familiar with already. So hopefully I can give you guys a few new insights. You all know my previous lectures have been given. I have one more next week. Last week I talked about gravity and why gravity is such a problem for particle physicists. I just want to go back over a little bit what we talked about, particularly since there is some motivation in there for why we talk about extra dimensions. Gravity is different than the other three forces. There are four fundamental forces: electromagnetic, weak, strong, and gravitational. Gravity is different because the quantity that determines how strongly a particle interacts with gravity is the same. It's just mass. It's the same as the quantity that describes how hard you have to push the object to get it moving. This is what I said was the equivalence between gravitational mass and inertial mass. And because of that, it leads to the curved space interpretation, where you can basically just think of gravity as being something that warps the background and therefore affects everything equally. Black holes are probably the most famous prediction of general relativity, which is this curved space interpretation. Hawking radiation from black holes creates what we call the information paradox, because it appears as though complicated objects can fall into a black hole, but once they're inside the horizon, the black hole is an extremely simple object. And when it radiates stuff out in the form of Hawking radiation, this is extremely simple, random radiation that doesn't include a lot of information. So it appears as though you have an irreversible process. And quantum mechanics has as one of its fundamental assumptions that any sort of particle by particle interaction should be reversible. You should be able to run the same thing backwards in time and still have a viable process. I talked about the fact that gravity doesn't just interact with mass. Mass is a form of energy, and what gravity is really interacting with is energy. Gravity interacts with all energy. And because of that, it cares what the background vacuum energy density is. And this creates a problem because quantum mechanically and in terms of the particle theories, you have all sorts of contributions to this vacuum energy, but they all seem to contribute a huge amount. Whereas if you actually go out and measure this background energy, you find it to be very, very small. And we can't explain it. It's a matter of 120 decimal places off. You expect a number on the order of 1, you get a number on the order of 10 to the minus 120. It doesn't make a lot of sense. Gravity quantization breaks down at high energies. Basically, this is because particles are point-like, and if you get really close to a point-like object, it looks like you put an infinite amount of energy into an infinitesimal point in space. And this doesn't make a lot of sense to us. Gravity is particularly bad like this. And string theory I introduced last week as the natural solution to this problem. If you've got a problem with objects being infinitesimal and all of this stuff focused on one point, why don't you take the object and you make it not point-like? You stretch it out in at least one dimension, and suddenly this energy gets dispersed and you don't have these really terrible infinities anywhere. So I introduced string theory as sort of the most two-dimensional objects can vibrate in a variety of ways. They can have shapes, and they can have internal movements. And these internal movements give the strings internal energy, and they give the strings internal angular momentum. And these things together mean that from far away, it looks like you have a different particle with a particular amount of mass and spin. So one string vibrating in a variety of different ways can give rise to what we observe as many different types of particles. So this creates a framework for unifying all of the particles we see in the standard model, potentially. And in particular, it predicts particles that would behave like, for example, gravitons and photons and gluons, which would mean that it would explain the strong force and the electromagnetic force and the gravitational force all together in a natural framework. Well, this is all well and good. We don't know for sure whether or not strings can solve the first two problems that I listed, the black hole information paradox problem and the cosmological constant vacuum energy problem. It looks like there's potential for them to solve those problems, but we don't necessarily have all the pieces. Now, one thing that I mentioned last week was the fact that string theory, as it turns out, doesn't make sense in three spatial dimensions and one time dimension. Physicists usually refer to this as 3 + 1 dimensions. What they mean is 3 space, 1 time. String theory doesn't make sense in 3 + 1. String theory, as it turns out, is only consistent if you have some larger number of dimensions. In the case of string theory, this is usually a total of 10 or 9 + 1 dimensions, 9 spatial dimensions in 1 time. There are certain extensions of string theory called M theory, which add yet another dimension. And I didn't really talk a great deal about the implications of that, but today, hopefully, you guys will get a sense for it. String theory is not the only possible reason to imagine having extra dimensions. It's a possibility that we, as scientists, need to consider and, ask ourselves, what would happen if this existed? String theory is one motivation for it, because if string theory is true, then there have to be extra dimensions. But certainly there could just be extra dimensions even if string theory is wrong. So I don't want to give you the impression that the only reason to think about this is strings. So today's topic is extra dimensions. I'm going to start out with some basic review of geometry. Hopefully you won't be too bored. A zero-dimensional object is a point. It has extent in no direction. Traditionally, you're used to thinking of a one-dimensional object as a line. It's completely straight. It goes on forever in one way or in the other. Similarly, a two-dimensional object would be a plane, flat piece of paper, and a three-dimensional object would be some volume. Now, our brains aren't terribly well designed to think about things beyond this, but you can certainly mathematically imagine extra dimensions, and these would create hypervolumes. So far, I'm basically assuming that all dimensions are exactly the same. They're completely flat. They just, extend out forever in some orthogonal perpendicular direction. And, in this picture, if there were 10 dimensions, then I could move forward, I could move to the right, I could move up, or I could move, and then my brain breaks. Because I don't know how to think about that. But there would be some additional direction that would be perpendicular to all of the others that I just named. Now, our experience of the universe is that it seems to have 3 spatial directions and 1 time dimension. Now, so how do we rectify this? How do we rectify our day-to-day experience of 3 + 1 with the idea that maybe there are more dimensions? The answer is, let's see if we can make the extra dimensions small. Well, what do I mean by that? Take just 1 dimension for now. Normally, this is a line. so on. I give you one number and you can figure out where I meant on the line. It's a number that goes from negative infinity all the way up to positive infinity. How do I make this small? A compact one-dimensional system is a circle. Now, I can describe my position on a circle, again, with one number. How far along the circumference am I? However, what makes a circle different than a line is that if I go far enough, suddenly I could describe this position by x equals L, but I'm actually at the same position as x equals 0. This, to me, is the most fundamental concept for a circle that there is. You go far enough around it, and you come back to where you started. Now, L is what I'm going to call the size of the compactified dimension. I'm really sorry about this word. Physicists, like any other sort of small field, we develop jargon. Our jargon is particularly evil, I think. We commit acts of violence towards the English language every day. This is just the word we use. I realize that it's not a real word, but it's the word we use anyways. So we say that L is the size of the compactified dimension. Suppose we're considering objects that move very, very short distances. And the movements that we're considering and the length scales we're considering are much, much smaller than L. This is like we're zooming in on the circle. And if we zoom in on the circle, what you get is something like this. You zoom in even closer, you get something that's just like in between there. And you see that the closer we get, the more the circle just looks like a line. At really, really short distance scales, you can't tell. I mean, this is something we, of course, have a day-to-day experience with. The surface of the Earth, to us, walking from here to the grocery store, is pretty flat. We know that over longer distance scales, you would notice that the surface of the Earth is actually curved, that it makes a sphere. But if you're not traveling too far, then you don't really notice this effect. So this is basically the same thing. At distances much smaller than L, the circle looks like a line, and this is going to turn out to be very important to us. You can do the opposite. You can ask, what if we're talking about distances that are much, much larger than L? Now it looks like we've zoomed out, and we're very far away from the circle. And what do you get? Now it looks like you have a point. So, let me just bring us back here. In this naive picture, I had 0 dimensions as a point and 1 dimension as a line. Then I introduced this idea of a compact dimension. And what I'm saying is there's a distance scale associated with this compact dimension. It's the size of this dimension. And if I'm looking at physics very, very small compared to it, I have the classical, most basic, simple one-dimensional object, the line. And if I'm looking at distance scales that are much, much larger than L, then I have the classical, most basic, zero-dimensional system, a point. So it's like the compact dimension, depending on how close to it you are, you either have 1 dimension or you have 0. Now, when we picture a circle, we picture it inside a plane. You know, you start with a piece of paper and you draw a circle on it. The piece of paper is your plane, and now it has a circle inside it. Basically what we've done is embed a curved one-dimensional object inside a two-dimensional surface. This is not actually necessary. It's possible to have a circle in only 1 dimension without the plane at all. This is tricky, but remember what I said was the most fundamental aspect of being a circle. You start in one place and you travel along it and you get back to where you started. That's possible without it's possible to say you have that without reference to a plane at all. That's the fundamental property. And this explains something. I told you that a circle was the way to compactify one dimension. Well, on a plane, it looks like you could do a whole bunch of things, right? You can have a perfect circle, you can have like a squished ovally circle, you can have an even more complicated, deformed object. But if you take away the plane that you've actually drawn these on, and all you're concerned with is whether or not you start in one place and then come back to where you started, all of these things are the same. Which is to say that if we really only have one dimension and then we compactify it, then we have one compact dimension, there's only one way of doing this. One dimension, compactify it, it has to be a circle. And by a circle, all I really mean is I travel around, I come back to where I started. This one's tricky. Our brains are not used to going here. Now, suppose we have two dimensions. One of them is compactified. Now what we have looks like the surface of a cylinder. And I want to do this zooming in, zooming out thing. I'm going to do this all day long. If I zoom in really close, then the surface of the cylinder just looks like a plane. Two full dimensions. If I zoom out, then it looks like the cylinder is really, really narrow, and the further away I get, the more it just looks like a line. One dimension. Again, the story here is the compactified dimension, depending on what distance I am considering, is either a full extra dimension or it disappears altogether. It's like it interpolates between two dimensions and one dimension, depending on what distance scale you're probing at. This is the general rule. If a compactified dimension has size L, then it scales much smaller than L. It looks like the dimension is not compact. It scales much larger than L. It looks like the dimension disappears altogether. And this is the key to how we rectify the idea that maybe there are actually 10 dimensions with our day-to-day experience of having only 3 spatial dimensions and 1 time dimension. We say, well, if these extra dimensions are compact, and if they have an extremely short distance scale, much, much shorter than, the meters and centimeters and millimeters we're used to sort of living our day-to-day lives at, then we simply wouldn't notice them at all. They would be basically gone at these length scales that we experience the world at. Now, suppose you have to compactify more than one dimension at a time. It turns out that while there's only one way to compactify one dimension, if you have 2 and you try to compactify them, there's an infinite number of ways of doing this. In this, even without reference to, and here of course we picture this, the sphere and the torus and so on embedded in 3 dimensions because that's the way our brains work, unfortunately. Even if we try to take them out of that picture and only have them without reference to the 3-dimensional volume, a sphere and a torus are fundamentally different. And one way of thinking about this is these previous shapes I have here. You can imagine squishing this circle in sort of a gradual way and turning it into this oval or this wiggly tri-star thing. But I can't take a ball and squish it and smoothly deform it into a donut. I would have to tear it at some point. That's one way of seeing fundamentally different objects, even without thinking about them in three space. There's an old joke, the subject of this, of what shapes are really fundamentally different from each other and what can be deformed into each other, is topology. There's an old joke that the topologist can't tell the difference between his coffee cup and his donut, because topologically they're the same. If you're compactifying two dimensions, then you basically get a family of possible compactifications that are described by how many holes. A sphere has no hole, a donut has one hole, this Mardi Gras mask looking thing has two holes. You could imagine a 3-hole object, a 4-hole object, and so on. And these are really the only ways of compactifying two dimensions, but there's an infinite number of them because you can have as many holes as you want. In more than two dimensions, it gets even worse. We don't really understand how to describe all the different ways of compactifying an arbitrary number of dimensions. But if we believe string theory and there are 6 extra spatial dimensions that we need to compactify and get rid of, hopefully I've convinced you that there are a variety of ways of doing this. And these different ways, I will be trying to persuade you as the day goes on, would lead to different physics from our 3+1 dimensional point of view. It would lead to different kinds of 3+1 dimensional particles and different behaviors for force laws and things like this. Now, let's talk about gravity and what happens to gravity when we think about extra dimensions. So, for the most part in this, I'm not going to need quantum mechanics, and I'm not even really going to need general relativity or the curved space. It's good enough to think about Newtonian gravity. Well, Newtonian gravity says that there's some force attraction between two masses, a mass m1 and a mass m2, that are a distance r apart. And the law goes gmm over r squared, where g is some constant that we call Newton's constant. Now, that means that the gravitational field about some mass m is gm over r squared. There's a picture that we can draw of this that's called the field line picture, where you draw lines coming out from the gravitational source, from the mass. And the regions where the field is stronger are represented by having more dense lines. As you go further away, the lines spread out, they're less dense, and this represents to us the fact that the field is weaker as you get further away from the mass. If you imagine drawing a sphere around this source, there's a question you could ask: how many field lines are going to pass through the sphere? This is called the flux of the gravitational field. And it's a measure of how much gravitational field there is on this sphere. Well, we'll notice that as you change the size of the sphere, it goes up and it goes down. The number of lines passing through the surface doesn't change. I mean, think about it. You can imagine building this with toothpicks and a bubble in the middle, and you grow the bubble. You don't actually get any more punctures than you would, because all of the lines that are out here are also in here. So the flux of field, the amount of gravitational field that passes through this sphere, stays the same regardless of how big the sphere is. The field gets weaker as you get further away, but at the same time, the surface area of the sphere gets bigger. So any given patch of the sphere has fewer field lines passing through it, but as you add up the entire surface area of the sphere, the two effects cancel out. And the way to see this mathematically is that the surface area of a sphere is 4 pi r squared for the radius of the sphere r. The strength of the gravitational field is gm over r squared. And if you multiply these two things together, you can see that this dependence on the radius, on how far away you are from the surface, disappears altogether. The surface area grows by just the right amount to cancel out how fast the gravitational field is dying off. Turns out that this is a very fundamental property of the gravitational field, and indeed of any field that is transmitted by massless particles. This is the key. This is the thing you want to hold on to. And the reason I say it that way is that suppose you actually live in a world with a different number of spatial dimensions. And it's easier for us to go down than it is to go up because we can actually picture 2 dimensions. So I'm going to talk about gravity in 2 dimensions. Now, you have gravitational field lines spreading out in a plane instead of in 3 space. And while in 3 dimensions the gravitational field source was surrounded by a sphere, now you just have a circle, right? It's sort of the 2-dimensional version of a sphere. And again, it has some radius r. We want the amount of field passing through the circle to stay the same, regardless of how big the circle is. Well, the surface area of the sphere should be replaced by the circumference of the circle. That's how much circle there is for field to pass through. The circumference of the circle is 2 pi times r, rather than r squared. And what that means is that the gravitational field shouldn't decrease like 1 over r squared, because then those factors won't cancel out. Instead, you need the gravitational field to decrease like 1 over r. So if instead you have a gravitational field that behaves like some new constant times mass divided by r, then this times this is again independent of the radius of the circle. So what I'm trying to convince you of is that if what we want to hold on to is this feature that no matter how big we make the surrounding surface, the amount of field passing through it doesn't change. The field doesn't disappear. The field lines don't evaporate or new ones don't grow. If that's the key, then by changing the number of dimensions we're considering, we have to change the way the gravitational force law works. That 1 over r squared is an artifact of the geometry of living in 3 dimensions. If you have a different number of dimensions, you should have a different force law. And in fact, in 2 dimensions, the law is 1 over r. Well, if we generalize this, if we have d spatial dimensions and 1 time dimension, and here's again where trying to visualize things will make you want to run and hide. What you call a sphere, we normally would call a 2-sphere in the world of mathematics, because it's the set of all points equal distance from a center in 3 space is a 2-dimensional surface. We want a d minus 1 sphere in d spatial dimensions. And I'm sure at some point you may have learned the surface area, which is the circumference of a 1 sphere, which is really a circle, is 2 pi r. The surface area of what you're used to calling a sphere is 4 pi r squared. You probably never learned the later ones, the 3-sphere and the 4-sphere and so on. I'm betting these did not come up in your high school geometry class. And the factors of pi and 8/3 and whatnot, who cares about them? The key here is that the circle circumference grows like r. In 2 dimensions, the sphere surface grows like r squared. The 3-sphere surface volume grows like r cubed. The 4-sphere surface volume grows like r to the 4th. And I'm sure you guys are noticing a pattern now. The important feature is that the surface hyperarea of a d-1 sphere increases like r to the d-1. And because of that, if you have a general d-dimensional system, the gravitational field should behave like some constant times the amount of mass at the center times what's causing the gravitational field divided by r to the d-1. Now, that's all well and good, and I hope I've convinced you that in a different number of dimensions the gravitational field should behave differently. But the topic of today is really about compactification. How does this story change if one or more of the dimensions we're talking about are compact? Well, again, we go to our two-dimensional picture because it's so much easier for me to draw. We try to draw the field lines around a gravitational force on the surface of a cylinder. And you'll notice something interesting. If you're looking at distances much smaller than L, which again is the size of the compact dimension, what you have looks like a normal gravitational field on a plane. This picture here and that picture here are basically the same. On the other hand, if I zoom really far out from the cylinder and I turn it into effectively a line, all I really have is one field line that goes up and down the line. This is, in fact, the gravitational field in one dimension. And what we see is that at distances much larger than L, the field looks like it would in one normal dimension. At distances much smaller than L, the field looks like it would in two normal dimensions. So the gravitational force law is actually going to change fundamentally as you go from a large number of dimensions of a large size to a really short size. The way gravity itself changes, changes. Suppose we live in d spatial dimensions, one of which is compact. Make life easy for us for now. With some size L, there's a gravitational source, a mass m, at some location, and you are at some distance r away from it. For r, at much larger distances, the gravitational law should go like 1 over r to the d-2, because it's like that compact dimension has disappeared altogether, and you live in one fewer dimension. At distances much shorter than L, that compact dimension is basically flattened out into a full dimension. You now live in full d non-compact spatial dimensions, and the law goes like 1 over r to the d-1. Now, if you imagine actually traveling from really far away from this point to really close to this point, you kind of get the idea the gravitational field shouldn't like jump randomly at some point, right? It should vary more or less smoothly. And it might vary like this and then suddenly take off, but it shouldn't do that, right? It shouldn't suddenly change by some discontinuous amount as you go from here to here. That doesn't make a lot of sense. For that to be true, the constant that's up that determines how strong gravity is, Newton's constant, in d-1 dimensions has to be different than Newton's constant in d, and it has to be different by just the right amount. If you look at the distance r, and if you stand at exactly the distance r equals L, where the behavior changes, where you go from sort of d-1 dimensions to d, then the gravitational field predicted by this equation should be the same as the one predicted by this equation. And what you see is that Newton's constant actually changes by a predictable amount. What I'm telling you is that if Newton's constant determines the strength of the gravitational field, then as you go from large distances to short distances, it looks like the fundamental strength of the gravitational force has changed. Now I'm going to do this in another way. This might be a little easier, and again I've chosen going from a two-dimensional gravity to a three-dimensional gravity. So it's like we have two non-compact dimensions and one compact dimension. And at long distances, it goes like gm over r, and at short distances, it goes like gm over r squared. And they match up somewhere in the middle. And you can see that I have the dotted line here is gm over r. What happens as I get closer to the source is that suddenly the gravitational field starts getting stronger faster than I thought it was going to. So if I imagine that there are 6 extra dimensions that are compact, and I really live in this 10-dimensional string theory world, then sure, the 1 over r squared law that we know and love works fine for the solar system. But maybe if I start probing, if I go down to the size of a couple of millimeters, and then I go down even further than that, and now I'm talking about atomic distance scales, as I get even shorter, it's possible that the gravitational force increases much faster than I thought it was going to, because it's actually going like 1 over r to the 8 at really, really short distances. The implications are that we thought that gravity is such a weak force that in order to really get to the regime where you have to consider quantum gravity effects, we thought we had to go to really, really high energy scales or really, really short distance scales. Maybe if there are these extra dimensions and they're compact, then as we get closer, the force of gravity actually gets stronger much faster than we thought it would. And maybe we don't actually have to go to quite such high energy to probe quantum gravity. If gravity really is much stronger than we think it is at really short distances, then maybe it's more accessible to experiment than we thought. Well, gravity is pretty well understood on the scale of the solar system. We've done a lot of experiments measuring how long it takes Venus to get around the sun and the Earth's orbit and the moon's orbit around the Earth, and these are all things that we understand really, really well, and they all have the gm over r squared classical Newtonian gravity law that we grew up with. It looks at these distance scales as if we have 3 spatial dimensions and only 3 spatial dimensions. Short distances, trying to explore the effects of the gravitational field at very short distances is really hard experimentally, because once you get down to really small objects, you're much more likely to have objects that have a significant amount of electromagnetic charge, for example. And the electromagnetic force is much, much stronger than gravity. And so your experiment is going to be 99.999% electromagnetic effect, and then this teeny tiny little gravitational effect at the end, which gets swamped experimentally and you can't actually see. Doing precision gravity experiments is very, very tricky. However, people have been doing this recently. They've taken this idea that there might be extra dimensions seriously. What they do is they sit down and they try to measure the gravitational attraction between 2 really small objects that are really close together. And they ask, is this a 1 over r squared force law or isn't it? It's, at the end of the day, it's a really simple question, right? They've gotten down to on the order of tenths of millimeters. And they haven't found any deviation at that distance. But that really leaves a fair amount of room. Now, there's sort of this naive thinking, well, there's no particular reason for the compact dimension to be one size versus the other, but there is sort of a natural length scale that we already know about. It's the Planck length, the length that you get by combining Newton's constant with Planck's constant with the speed of light. That's a natural length scale for interesting things to happen at. The old thinking assumed that if there were compact dimensions, they would be on the size of the Planck scale, which is really, really tiny. Very, very small. But there's no actual experimental evidence that it has to be that small. And when there's no experimental evidence, sometimes you have to sit down and say, well, let's run some experiments then. Let's not assume anything, because that's always a bad idea. We're looking for as many as 7 possible extra dimensions if you're in theory and you have 10 plus 1. And they're not even necessarily compactified on the same distance scale. I mean, you could have a torus that's really skinny but really big, right? So, one of the classic things that people talk about when we talk about extra dimensions is the creation of tiny little black holes. Well, if you assume that there are 3 spatial dimensions, the horizon of a black hole is given by Newton's constant in 3 spatial dimensions times the mass divided by c squared. This gives you the distance scale. And again, I talked about this a little last week. The picture here is that at the LHC you have a proton over here and you have a proton over here, and you're throwing them at each other really hard, and if you can give them enough energy, then as they fly by each other, maybe they're really close together, and if they're so close together that their total mass is inside this horizon, then you've created a black hole. Well, you can ask yourself, how much energy do I need to give the protons to do this? Well, the mass would be just 2 times the mass of the proton, and certainly we know what the speed of light is in Newton's constant, and I can convert this distance to how much energy would be required to get the protons that close together by hc over r. I plug in the numbers, 5 times 10 to the 35 TeV. Well, the LHC is running at 14 TeV. So that doesn't look terribly likely. But let's see what happens if we imagine that there are extra dimensions. Suppose that there are really 10 dimensions, and the 6th volume of the compactified dimensions is some V6, which is like L to the 6 for the various lengths. The horizon of the black hole in 10 dimensions is not this simple formula. It's something much more complicated. The gravitational law is G9 times m over r to the 8. And you can just sort of dimensionally realize that in order for this to be a force, the dimensions of Newton's constant have to be different. And the combination of Newton's constant and the mass and the speed of light that gives you a length is this awkward power to the 7th, to the 1/7. Well, the 10-dimensional or 9 plus 1-dimensional Newton's constant is related to our observed 3-dimensional Newton's constant by the size of compactification in order for the gravitational field to vary smoothly as I go from long distances to short distances. And again, I wind up with this formula. I don't know what the volume of the compactified dimensions are, but I can plug in some numbers that are well within experimentally observed values. And for example, if I imagine that the compactified dimensions are each on the size of 100 femtometers, which is much, much smaller than the best precision measurements exclude, then the required energy is suddenly only about 8 TeV. And now we're creating plenty of black holes at the LHC. So you can see that these extra dimensions, they really affect what's possible. big they are, you can go from not happening, never in a million years are we going to create this on Earth, to, oh yeah, next month.
Question.
Yes?
What keeps a small black hole from getting bigger?
So there are two effects that are possible, right? It's, on the one hand, it's a gravitational attractor, so it tends to gravitationally pull things in. But remember, it's actually very light. It might be a black hole, but its total mass is only 2 times the mass of the proton. So it's not a particularly strong gravitational source. On the other hand, it's also Hawking radiating. And so what happens with a really small black hole is that it winds up radiating away all of its energy and disappears long before it pulls stuff in. Yes?
Quite small. What if you, any of these arguments about the laws of gravity going bigger and accounting for this dark matter, dark, gravity acts differently as galactic.
Okay, so you're asking a different question, which is, I'm talking about whether or not gravity acts differently at really short distances. He's asking, what kind of evidence do we have of how it acts at really, really big distances? And the answer is, of course, there aren't a lot of direct measurements you can do, but at really long distances. I mean, really, it's observational astronomy, and a lot of it assumes a form for gravity in order to do.
But you have the evidence of dark matter.
But dark matter doesn't involve changing the way gravity works. It just involves having gravity. I mean, all dark matter is mass that doesn't interact with photons. It's dark. You can't see it. It's not giving off photons. This is not really this isn't really a correction of gravity. It's just there are particles out there that have mass that don't interact strongly with photons. All it involves is having a new, different kind of particle. So, why am I talking about gravity? Why this whole big spiel I gave about the gravitational field and the geometry and the spheres and whatnot, why can't I substitute an electromagnetic field and make exactly the same arguments? Well, it's possible to imagine a scenario where we live in some three-dimensional membrane that is embedded in some higher dimensional volume. So right here, of course, I have a two-dimensional plane and a three-dimensional volume because I can't draw 4 dimensions. But it's possible to imagine further that certain particles, for example, photons, are constrained to only travel along this membrane. So they would be completely three-dimensional, and the electromagnetic force simply wouldn't notice the extra dimension at all, ever. It would only travel in 3 dimensions. On the other hand, gravity is the curvature of space-time. The curvature is the way these dimensions are shaped, and that is the gravitational field. It's not possible to confine gravity to the membrane. If there are extra dimensions in any sense, the one force we know has to be affected by them is gravity. Maybe the other forces are, and maybe they aren't. It's possible, maybe not. Gravity has to be. So if you're really looking for extra dimensions, gravity is the way to go. You look at gravity because it's the one that has to be affected. Now, I'm going to bring in one last thing. Well, okay. That being said, it's certainly possible to imagine a particle of some type that travels in a system. For example, we again have this two-dimensional surface where one dimension is compactified, and it travels both in the compact direction and along the normal non-compact direction? Well, again, close to the surface of the cylinder, you have basically the particle traveling in a straight line. There's no forces acting on it, so it's just going to go and go and go along where it starts. As you zoom out, what you see is that this straight line is really a spiral around the cylinder. It goes zoom. Well, at really close, it looks like a straight line. Really far away, you don't see that it's traveling around a cylinder. All you see is that it's moving down a line, right? All you see is its motion in the one dimension you have left. Well, the particle might be traveling very fast, but have most of its motion around the cylinder. This is like a really narrow, tight spiral that it's traveling in. It has a lot of energy associated with this motion, but from far away, when you're looking at it from the one-dimensional long-distance point of view, it doesn't look like it's traveling very fast. This energy from motion in the compact direction becomes mass. It's some internal energy, therefore it's mass. One type of particle traveling on the cylinder from far away looks like a variety of different kinds of particles with different masses traveling on a line, depending on how much motion it has in the compact direction around the cylinder. Now, the amount of momentum in the compact dimension turns out to be quantized by quantum mechanics. And what this does is, instead of just giving you any arbitrary mass that you want, it gives you a discrete set of masses. It can be traveling this much in a compact dimension, and that'll give you mass M1. It can be traveling a little bit more, and that gives you mass M2, and so on. What you see is one kind of particle traveling on the cylinder looks like a set of particles with a range of masses traveling on a line. This is called the Kaluza-Klein Tower, after the two guys who first worked with this kind of system. And the array of masses will depend on the shapes of the compactified dimensions. Because depending on how it's shaped, it can have different kinds of motion, and that'll create different patterns of masses from our lower dimensional point of view. So this is another part of the story of a signature of extra dimensions. If we live in 10 dimensions and 6 of them are compactified, then we should see these arrays of particles that look very similar to each other, except they have increasing amounts of mass. Because actually, it's the same particle, it's just traveling a different amount in the extra dimensions we don't see. So, to summarize, one compact dimension is a circle. Compactifying more than one dimension can happen in a variety of ways, and if there's one sort of big moral I want to bring home, is that this compact dimension has a distance scale. And if you're much smaller than this distance scale, then it looks like you have the full number of dimensions and they're not compact. And if you look at it from a very far away, much longer distance scales, then the compact dimensions basically disappear and you're working with a lower dimensional system. In 3 dimensions, the force of gravity behaves like 1 over r squared, but if you change the number of spatial dimensions, then the law of gravitational attraction changes. Its dependence on distance is 1 over r to the d minus 1 instead. That 1 over r squared is a geometric fact that depends on how many dimensions you're in. With compactified dimensions, the strength of gravity changes as you go to shorter distance scales, and in fact it grows stronger. So if we live in 10 dimensions, but 6 of them are really small, then at really long distance scales, we have this 1 over r squared force law, and gravity is very weak. But as we get much shorter distance scales, and in particular as we get to distance scales that are small compared to the size of the compactified dimensions, suddenly the gravitational force gets much, much stronger, much faster than we think it's going to as we get closer. I talked about the fact that depending on the size of the compactified dimensions, it's possible that this could lead to some effects where you see strong gravity, even at, for example, the LHC, and this could lead to the creation of black holes at the LHC. And then finally, and while it's true that gravity is the only thing that really has to be affected by the existence of extra dimensions, if you imagine there are other particles that can travel in these compact dimensions, then their motion in the compact dimensions gets expressed, the energy associated with that motion gets expressed as mass in the lower dimensional system. And what you see is Kaluza-Klein Towers of particles of different masses in our lower dimensional world. So that is today. Weird subject to wrap your brain around. Yes?
Your last bullet point here creates a tower, the Kaluza-Klein Tower of particles of different masses.
Yes?
Does that mean, is that referring to all the subatomic particles we were looking at?
Yeah, it means, for example, you have a proton, and now you have a much more massive particle that, other than that, really behaves very similar to a proton. And then you have an even more massive particle that also behaves very similar to a proton. Yes?
It seems like we're assuming that there's one length scale per dimension that can be compactified. But when you get to objects like that mass, mass that we had up there, the double torus thing, is one number really enough to quantify one per dimension? Is that enough?
There are pictures where it wouldn't necessarily be. For example, you don't even really need more than one compactified dimension. You could imagine, instead of a cylinder, what you have something like this. It is definitely possible. So from really, really, really far away, this is still a line. But depending on where you are in this direction, the compactified dimension is a different size. So it's definitely possible for there to be more than one length scale associated with one dimension that's been compactified. This is it's a simplifying assumption that it's not going to change by too much. You can certainly expect that if it does change by a lot, there should be some good reason for it. Yes?
Why 10 dimensions instead of some other number?
There's no short answer for that. The best I can do is say that it's definitely 10. The math says 10, and it's not math that I can show you in a convincing way. Yes?
On that second to last bullet, if a black hole is created in LHC,
Yes?
does that then mean we've seen the extra dimensions?
Pretty much, yes.
Okay.
There's really no way to imagine, well, okay. I suppose it's possible that the law of gravity suddenly goes from 1 over r squared to 1 over r to the 8 for some reason that has nothing to do with extra dimensions. But this would be very, very odd, and certainly the simplest answer would be that we have seen extra dimensions. Yes?
Just to follow up on the last item, have we seen particles that create partial towers to date, or are we still awaiting experiments to show us that?
Not really. I mean, it's hard to know exactly what a tower would look like. So you know, if you have the most simple case where the compactified dimensions are just perfect circles, then the towers are completely even, and this would be impossible to miss experimentally. But the moment you start having, you know, spheres and toruses and wibbly wobbly objects, then suddenly this experimental signature is much, much harder to figure out.
Different kinds of bullet. That was one example of a tower.
What was that? He wants to know so the particles in the standard model fall into generations. There's there's an electron neutrino, and an up quark and a down quark, and then at the next level there's a muon and a muon neutrino and a strange quark and a charged quark, and then there's an even more massive tau and tau neutrino and top and bottom quarks. He wants to know if those generations are signs of this Kaluza-Klein thing. We don't have a coherent model that would explain the generations using extra dimensions. Let's say it that way. You're right that generation pattern is very interesting, and you want to explain it because there's no naive reason why there should be copies like that at increasing masses. But certainly the details are just not known to explain it fully. Yes?
So if you know that the universe is expanding, but it's not expanding from one point, doesn't that kind of prove that there has to be another dimension?
So, not really. The best picture anybody ever gave me for picturing the expansion of the universe is picture a balloon that's being blown up. And in this image, the surface of the balloon is the universe. And you can draw stars or galaxies on the surface of the balloon. And from the point of view of the surface of the balloon, it's not like there's one point on the surface from which the whole thing is expanding. It's just all of the points on the surface of the balloon are coming apart at once. That doesn't really require that there are extra dimensions at all for that picture. It's just, you know, some two-dimensional surface that everything is flying away from each other. I'm not sure if this is going to help you visualize it. These are pretty hard to visualize, but it's usually the one that people say. Yes?
Does extra dimensions help explain things like particle entanglement?
Not to my knowledge, no. Yes?
Has there been any experiments that support compactification?
No, we have no experimental evidence of extra dimensions to date. Yes?
So Higgs be put in this scenario. How do you interpret these terms that Higgs put?
Well, I would imagine it was probably the lowest particle in a Kaluza-Klein Tower of Higgs bosons.
Responsible for the
Yeah. Well, I mean, the story that they give you that the Higgs is the origin of all mass is a little naive because actually there are a variety of ways you can get mass. You can get mass from binding energy, you can get mass from motion in an extra dimension, you can get mass from interacting with the Higgs field. These are different things, really. Yes?
Why do you say that gravity increases at smaller scales? Because if the denominator has increased dimensions,
Right.
it should be weaker because it's in the denominator.
Yes, but the number that's in the denominator is really, really small. So it's like 1/10 is 10. 1/10 squared is 1/100, which is 100. So that's even bigger. You see that? Yes?
I think you must have answered this and it went right over my head. But I'll ask anyway. If 10 dimensions is the
problems with combining gravity with quantum mechanics that string theory solves at least some of and may solve all of. String theory itself, however, requires 10 dimensions in order to make sense. And that's, again, that's a thing that I can't really show you. But mathematically, string theory requires these extra dimensions. So if string theory is the solution to the problems we know about quantum mechanics and gravity, then we have to find the extra dimensions. Yes?
Leaving apart neutrinos, would string theory say that a muon and a tau are simply an electron or something smaller than an electron that has faster internal motion?
Not necessarily, although, again, it's possible. This is a question about the origin of the generations of particles in the standard model. I've had one person ask whether this could be a Kaluza-Klein tower, and now you're asking whether it could be strings with different kinds of motion. The answer is possibly yes, maybe. We don't have a coherent model that explains exactly how to get the standard model out of strings, so we don't have all the answers on this one. Yes, very far in the back.
Can we compare the relative strength of gravity through compacted 10 dimensions with our own, say, strong force in our dimension?
Well, okay, so remember what's really happening is we're getting to shorter and shorter distance scales. So the question is, if we get to the distance scales where gravity suddenly gets much stronger, whether or not gravity will suddenly be stronger or not stronger than the strong force. It depends on, in large part, for example, on whether or not the strong force is confined to 3 dimensions or whether it is also affected by the extra dimensions. And these are, very crazy ideas that we don't know a lot about their actual reality, so I don't know. Yes?
You said string theory requires 10 dimensions, but then M theory adds this one more. What is that doing for the theory?
It takes the fundamental objects from being strings to being more arbitrary extended objects in some ways. Yes?
You want gravitational force to change continuously as the distance scale changes.
Yes?
If electron orbits in an atom can jump in a quantized way, why can't gravitational force jump?
Okay, it's true that the orbits of an electron and an atom change in a quantized way, but the actual electromagnetic force doesn't. As you get if you ask what the strength of the electromagnetic force is as you get closer and closer, it's continuous. And again, part of this is there's a disconnect between the fact that I used classical Newtonian gravity and you're talking about quantum mechanics, but in general, the underlying force law has to change continuously, even in a quantized system. Yes?
In order to verify this kind of gravity, what is the particle on which we should do experiments? I'm making a guess. Neutron would be just has no charge, right? That's the one.
Well, okay. At the LHC, they're using protons. Because they're just trying to create, the idea of trying to create black holes will work with any kind of particle, right?
No, but the idea is just to study gravity.
But you mean the tabletop experiments? You mean the tabletop experiments?
Yeah, something like that, yeah.
What you usually want is probably, now I don't know the details of these experiments, but my guess would be you want things that are simple. And
so I figured neutron is simple because there's no charge.
A neutron is simple except that it's really 3 quarks and it has a lot of strong force inside it. That's a little, and we're at distance scales where that might matter. So it's tricky. The other route to go would be to pick an object that definitely has charge, but to work with electrons, but we really know what the electromagnetic force does, so we just take that into account. Yes?
What you've done today doesn't explain the seeming breakdown of Newtonian gravity at very, very large distances where you take a galaxy and things are moving at speeds they shouldn't be moving at.
This is the same question that got asked earlier. It's not really a breakdown of Newtonian gravity. It's what he's referring to is the fact that if you look out at a galaxy and you measure how much mass it has based on how bright it is, there's, you say, given that it's giving off this much light, there should be this many stars in it, and they should have an average mass of such and such, and therefore the galaxy is this massive, and you look at how big it is and what it's shaped like and how it's spinning, and you compute it, and it doesn't make sense. Newtonian, in terms of the Newtonian law of gravity, it seems to be spinning much too fast. What this tells us is that there's more mass in the galaxy that we don't see.
Well, that's your dark matter.
That's dark matter. All the, dark matter is this. I'm not sure why people get so very excited about it. Really, dark matter is matter that's dark. It's something you can't see because it doesn't interact with photons, but it still has mass. So it's still affected by gravity. So it doesn't really require that gravity changes at those distances, just that there's something there that we can't see.
It's called temporal exist, and that gravity does cause gravity.
Yeah, okay. It's possible to hear hoof beats and decide that it's a zebra. But in general, I think it's more likely that there's simply particles that don't interact with photons. I mean, we already know some particles. Neutrinos don't interact very strongly with photons. Now, neutrinos, as it turns out, are not a particularly good candidate to explain most of the dark matter that's out there. But it's very possible to imagine that there's something else. I mean, all you need is a particle that doesn't interact strongly with photons, and there are a billion ways of getting that. Yes?
Something that's never mentioned about dark matter is you can't see it because it doesn't radiate. It has to be transparent or it would obscure the light.
Well, okay. So this is... This is about what the word transparent means. Here I have a blob of dark matter. And here I have a star. And here I am with my telescope up to my eye, right? Here's a photon. If the blob of dark matter doesn't interact with the photon goes straight through it. It is by definition transparent. Now, if the blob of dark matter doesn't interact with photons, that also means the blob of dark matter itself won't be giving off photons. It's both. You see that? Yes?
What if two photons take up more space than the volume of the horizon of a black hole of a mass of two protons? And so you could have explanations that would just fail because photons aren't dense.
The protons themselves. Well, the protons themselves are made up of quarks. And in this scenario, you give the whole system so much energy that it's like, I guess you could, a good picture for a proton is the bag of marbles picture with the quarks inside it. It's like you've given them so much energy that all the quarks are squished together too. If that makes sense, that the whole thing is much smaller than it would have been otherwise.
So
And the quarks themselves are, at least in principle, point particles or strings, but the size of the strings should be really small. So really, it's almost like the proton itself has become more dense, yes. LHC. This is, I mean, this is one of those things that we lie awake and dream about as this fabulous, wonderful thing that could come out of it, but I don't think it's terribly likely. I mean, it's much more likely that the size of the compactified dimensions, if they exist, is much too small. And, you know, it might not be 10 to the 35 TeVs that you need, but it could very well be 1,000, 2,000, 10,000, 100,000, you know, all of those numbers in between 14 TeV where we are, and that, you know, really high number where we would absolutely have to create black holes. Yes?
You missed your last two questions, though. You're going to talk about quantum gravity, quantum loop gravity.
Am I going to talk about quantum loop gravity? No. I don't believe that quantum loop gravity has much validity as a theory.
Why is that?
Because it fails to reproduce even the most basic things that we understand. For example, it can't reproduce special relativity as any kind of low energy limit. And to my mind, I mean, in history of science point of view, first you have Newton, and then you have special relativity. But special relativity, part of special relativity making sense is that at really low speeds, it disappears and reproduces Newton. You know, and then you have quantum mechanics, but part of quantum mechanics making sense is that at longer distance scales, those effects disappear and reproduce Newton. I mean, when you come up with a new theory to explain really high energies or really short distances, it should fold back into the original picture when you're at human-sized distances. And quantum loop gravity can't do that. It can't, even at really low energies, it can't explain the world that we know exists. And to me, that is a deal breaker. It's a theory I'm not interested in because it just doesn't make any sense to me at all. Yes?
Would I be correct if I said that all of the subatomic particles in standard model we've been talking about, those are all things that are identified and mathematized within a 3D universe?
Yes. The standard model is understood in terms of 3 dimensions.
And that no one has ever created a bunch of string theory mathematics to plump on top of those, or is it just that it works for string theory because you've got 3 dimensions and all the other ones are compactified, and it doesn't.
That's basically what the story is. That there's a way.
So the standard model can be explained by string theory.
In some. We don't know all the details, would be the best way. We have the big picture, but we don't have all of the steps. We don't know exactly how to compactify the extra dimensions. We do know that if you compactify them, then at long distance scales, they disappear and we have 3 + 1 dimensions. And that is, again, this is the human-sized world that we want to reproduce at, human-sized levels. But, all of the steps aren't there. If they were, then I might be out of job. Yes?
Perhaps you already answered this question when you were talking about 10 dimensions, and this question about M theory, but why are strings, one-dimensional strings, and not 2-dimensional membranes, or 2-volt boron?
It's a good question. The shortest answer is, if you imagine that the problem is an infinitesimal object, a point-like object with a lot of mass and, charge and whatnot in it somehow, and this is a problem because it's infinite, then the first thing you should try is stretching it out in 1 dimension. And then if that isn't enough, then you can try stretching it out in a second and make it a little plane. And if that isn't enough, then you can try stretching it out in a 3rd dimension and so on. And it turns out, in fact, that we got a huge amount of structure and all sorts of explanations, and not to mention the solution to the problem, just by stretching it out in 1 dimension. It's enough of an answer. And it's a bit of an Occam's razor thing. You try try the simplest thing first. And if that doesn't work, then you try the next most complicated thing. Yes?
Recently there was some topology, right, I think Poincare conjecture, which has something very similar to Einstein's theory, right? Using some kind of, I read an article in the New York Times about Ricci flows, or Ricci flows. Ricci flows. What's the impact of that to string theory? Because it's also based in topology, right? Did it help it in some way or weaken it in some way?
Well, I mean, it's a mathematical theorem about the way n-dimensional objects behave topologically. And so it helps us because, I mean, it helps us understand the mathematical structure. It's not really a physical principle, but, you know, like knowing that the circumference of a circle is 2 pi r, it helps. Yes?
Would a black hole have an unambiguous detectable signature?
Yes. The short answer is, so I talked a little bit about Hawking radiation and about how simple it is and how random it is. It's very much like the pattern of how light radiates off of a temperature object, like a hot object. If you look at the pattern of how much energy at different wavelengths comes off a light bulb, it's got a very distinctive spectrum, which is, well, we say it's completely thermal. It's determined almost completely by the temperature of the light bulb. The way particles radiate off a black hole is very thermal in the same way. It looks very much like this. And I mean, really what you have is you smash 2 particles together, they form some object, and then they decayed into some other stuff. But the decay pattern looks thermal, and it's very, very distinctive. It should not be missable. If we create them at all, we should know it.